So this is one thing. The other thing is about quiz number 1. So number 1 is going to be on Tuesday. It's going to be cover chapter 1. I sent you an email to give you the specific things you need to study for the quiz. Okay. Any questions? Good. So I want to continue on what I did last time. Okay. So as I explained last time, if you have in-bit number, this in-bit number can have 2 to the power of n different numbers of the different combination. Okay, 2 to the power of n. And then I told you if this number is unsigned number, that means in in-bit number I can store numbers from 0 until 2 to the power of n minus 1. This is a minimum, this is a maximum number. Okay, if the number is signed, so you can store numbers from negative 2 to the power of n minus 1, okay, until all the way until positive 2 to the power of n minus 1 minus 1. Okay, so negative is one more than the positive. That's what I told you last time. This is general for any value for n. Is that okay? So the most important thing you can learn here is for n-bit number, I have a limit about how big the number I can store in any bit. I have a limit. You got what I'm saying? You can't store more than that. For just quickly, as an example, if n is 16 bits, if n is 4 bits, so in case of unsigned numbers, I can store from 0 until 15. Okay, so the maximum number I can represent, or I usually use the word store, okay, not represent, because again, I'm thinking hardware. So I have a hardware any bit. So what is the biggest number I can store in any bits? Okay, anyway, or represent if you talk about a number in general. Okay, anyway, so the maximum is 15. Is if your number is between 0 and 15, so n bit 4 bits should be enough. However, if your number is greater than 15, so if it is 16, 17, anything else, so you need bigger space. 4 bit is not enough. You need something bigger than that. Okay. So the next thing I'm going to teach now is something we call it overflow. So I want you to understand what is overflow. Okay. So actually, if you have hardware circuit, this circuit can do addition, and then I have two input numbers. Okay, so the first number, we have 2 numbers here. The first number is stored in a register. This is a hardware. I'm going to explain in this course. A register is a hardware circuit that can store n bits. So here n bits is stored in a register. Same thing here. I have n bit stored in a register, a hardware, and then the result is going to store. I'm going to store the result also in n bit register. Is that okay? So this is a register. Register is a hardware circuit that can store certain number of bits. Okay, because it is hardware, it can only store n. It can't store n plus 1 because it's hardware, right? Every bit has a hardware to store it. Okay. Anyway, so what do you mean by overflow? So I have a hardware circuit like this one. So what do you mean by overflow? Very simple, very easy. Look at the English word overflow. Overflow in English means you exceed the limit. There is a limit and you exceed the limit. That's how it is. Okay. It's the same thing, exactly same thing here. If you have a number here that is in n bits, and then you have a number here in n bits, and I'm going to add these 2 numbers together. Okay. It may happen that the result is going to exceed the limit I have here, which is n bits. You got what I'm saying? For example, I give you a very simple example. I told you in case of n is equal to 4 bit. So for example, if I have here number 14 plus 7, okay? So 17 plus 7 should be 21. Can I store 21 in 4 bits? The answer for sure, no. So in this case, overflow happens. So overflow means I want to store the result in a certain space, okay, which is n bits, but this is not enough. You got what I'm saying? Because the number get bigger. Here, the number was enough to store it in n bits here. It was enough to store this number here. However, after I did addition, the number get bigger, right? That's why overflow can happen. That's why you are seeing if the two numbers you are adding have different sign, can overflow happen? If they have different sign, one of them is positive, the other one is negative. Can overflow happen? It can't happen because the number is not going to get bigger. You got what I'm saying? So overflow only happens when the two numbers have the same sign, positive, positive, or negative, negative. Because in this case, okay, they are going to assist each other. It's going to get bigger. Is that okay? So that's why it is known if the two numbers have different signs, so overflow cannot happen. Okay. Any question here about the concept of overflow? Okay. So think about it. When overflow happens, if overflow happens, so the number you will get here is going to be a wrong number. You got what I'm saying? The hardware doesn't understand, right? The hardware is going to just give you a number and then it's going to indicate, it's going to tell you there is overflow. Okay. So the number here, because you need 5 bits, but you actually, store it in 4 bits. So the number you will get is going to be wrong number. So that's what we call overflow. Is that okay? So what I'm going to teach now is how can you know if there is overflow or not in 2 cases, if the numbers are signed or unsigned. Okay. So if the numbers unsigned or the numbers are signed, I know students always confused between signed or unsigned. I made it very clear. Signed or unsigned, it is different hardware for signed or unsigned. Is that okay? And then the programmer, you can select which instruction you want to use, the one for signed or one for unsigned. Okay. But if I give you a number and you ask me this number signed or unsigned, I can't tell. It's not it's not written in the number. I can't know from the number if it's signed or unsigned, right? But for sure, if I give you a number and I tell you this number is signed, I can easily tell if this number is positive or negative because I'm going to look at the most significant bit, or we call it the sign bit. If it is 1, that means a negative number. If it is 0, it is a positive number. Anyway, so now I'm gonna explain how can you tell if there is signed or if there is overflow or not. Okay, so in case of unsigned numbers, so if I add the numbers, for example, something like that. Normal addition, if you do normal addition, 0 plus 1 is 1, 1 plus 1 is 0, and then we have 1 here. 1 plus 0 plus 1 is 0, and then we have 1 here. 1 plus 1 plus 1 is 1, and then we have carry here. Okay, so very easy, very simple. If you have unsigned numbers and you do the addition this way, and there is a carry resulted from the most significant bit. If there is a carry here, this carry is if the carry is 1, okay, that means there is unsigned overflow. Okay, if the carry is 0, so there is no overflow, unsigned overflow. That means the number you will get here is going to be a wrong number. Okay, and let's do it here. This number is simply 15. This number is actually 1, 2, and 4, 8. So this number is 10, right? This number 10. 10 plus 15 should be 25. However, the result I got here, don't be confused. The carry you get here is not a part of the result. Okay, it's the result is the 4 bits we have here. Okay, so you add 4 bits plus 4 bits. This is the result. This is a carry. I know you may be confused because when you do numbers, if they are numbers, this carry you can take it as a part of the result. Okay, but here look at it as a hardware. Okay, so you add 4 bits plus 4 bits, and then I'm gonna take only 4 bits. This is the result. Okay, anyway, so here, so I should get, if it is correct, so 10 plus 15 should equal 25, but what I got here is actually 1 and 8. I got in number 9. Okay, so which is not correct. So make it very simple, very simple, because this will be a question in the quiz. Also, it's going to be a question in test number 1. I'm going to give you like what I did here. I'm going to give you 2 numbers. I'm going to ask you number 1 to do the addition. Okay, number 2, I'm going to ask you, is there overflow or not? That's it. And I'm going to tell you this number is unsigned. Okay, all what you have to do the normal addition and then look at the carry from the most significant. If there is a carry, is that okay? So that means the number, there is unsigned overflow. If there is no carry, that means there is no overflow. And if there is no overflow, so the result here is going to be correct. correct result. I can give you for this case. For example, if I want to add this number 001, which this 3, number 3. So I'm gonna add it to something like that, which is number 8. So I'm expecting the result should be 12. Okay, sorry, 11. So let's do the addition. 1 plus 0 is 1. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 1 is 1. And there is no carry. So the carry here is 0. Okay. So if you look at the result here, because the carry is 0, so there is no overflow. That means the result is correct. Let's see. So this is 8. This is 2. And this is 1, which is 11. So it should be correct. Okay, guys. So when I ask you, I'm going to tell you about something funny. So when I ask you this question in exam, the easy way to do it, okay, is just to do addition, do the normal addition. If there is a carry resulted from the output, so there is overflow. This is the easy way, right? I found some students overcomplicated the problem, okay? So what they did, they converted this binary number to a number. They converted this one to a number, and then they converted this one to a number. And if the result is correct, so there is no overflow. If the result is false, it's not correct, so there is overflow. This is true, this is not false. But you overcomplicate it because to convert these numbers to decimal is going to take some time and you may make mistakes, whatever. You understand what I'm saying? So still this is a valid approach, but this is not the easy way. The easy way is just to do the addition and see if there is a carry or not. That's it. You understand what I'm saying? Any questions? Okay. This is in case the numbers are unsigned. Okay. Now, if the number is signed number, okay, I'm going to tell you again about a very easy approach to do it. It's very simple. For sure, if I add a positive number to a negative number, don't think about it. If the sign is different, don't even think about it. There is no overflow by common sense, right? Because the two numbers are not going to help each other. So if the sign is different, there is no overflow. Overflow may happen when the two number you add positive to positive or you add negative to negative. Okay, may happen. Okay, so what the easy approach I'm going to tell you here is, if you add a positive number to a positive number, and then if you look at the result, you find the result is a negative number. Okay, or if I add negative to negative and then I find the result a positive number. This is the only two cases that can make overflow. Okay, guys, so I'm gonna make it very easy. So again, do the addition, but be careful. The carry you are gonna get here is not a part of the result. Don't take it as a part of the result. The result here, this one is 4-bit, 4-bit. This one should be also 4-bit. Okay. So all what you have to do here, in case of signed numbers, okay, just to do the addition. Okay, very easy. And then the only two cases that can make overflow is these two cases. Okay, so if you don't have these two cases, there is no overflow. Very simple, and the result is correct. Okay, so again, the two cases is I add a positive number. Positive number means the most significant bit is 0. Positive number means the most significant bit is 0. But when I look at the result, I find the most significant bit is 1. So this is one case. The other case here is the most significant bit is 1, negative. The most significant bit is 1, and then in the result, I got the most significant bit is 0. Okay, can I add positive number to positive number and I get a negative number? That doesn't make sense, right? Yes, because it's wrong, because of overflow. You got what I'm saying? That's why this happened, because it's wrong, overflow. Okay, is that easy, guys? Please don't lose easy marks in this course. Okay, I'm telling you how you do it. It will be in the quiz, it will be in the test as well. I will give you two numbers, okay, and you have several examples here. It's just very easy. Okay, you have just if you understand what I'm saying here, it's going to be easy to know if there is overflow or not. Okay, so yeah, so here I'm explaining the concept of overflow or what overflow means. Okay, so here I'm talking. That's exactly what I explained about unsigned numbers, as you see here, and actually. For example, here I'm considering this one like 5 bits, 1, 2, 3, 4, 5 bits. So this is all the number we can have for 5 bits. So if you have here 5 zeros, so this can make 0 all the way until 5 ones, which can make 31. This is a limit. This is a minimum and the maximum. For sure, this one is actually 2 to the power of 5 minus 1. Is that okay? Look here to this point. If you have 1, 1, 1, 1, 1, 5 ones, which is 31. Okay. If you add 1 to 8, the result is going to be 0, 0, 0, 0. So actually you cross this boundary here. And at this moment, when you cross the boundary here, overflow happens. So that's why overflow can happen by the hardware, because if you have 1, 1, 1, 1, you add 1, you get 0. It's like it rules back. You got what I'm saying? So after 1, 1, 1, you add 1, you get 0. Okay, that's why overflow happens. That's why here I'm explaining. This is the boundary, is here. Every time you cross this boundary, after you add numbers, so actually overflow can happen here. And that's exactly what happened in this example here. In this example, you have this number, which is actually this number here, which is 28. This number is 6. I added the two numbers together. And because this one is 5-bit, the result is 5-bit. I repeat it multiple times, guys, because I know students are confused here. The last carry is not part of the result. You add 5 bits, and then the hardware is going to make 5 bits. You got what I'm saying? So that's what I mean by result. As a carry here, we call it carry. Okay. Again, as you can see here, because there is a carry resulted from the most significant bit. So there is overflow here. And you can see if I add 28 plus 6, I got 2. I got number 2. Okay. And how this happened? I'm going to tell you how this happened, because what happened is that I started from 28. So I was here. And then I added 6. I added 1, 2, 3, 4, 5, 6. That's why I ended here. You got it? This is a problem. If you are 1, 1, 1, and then you add 1, you are gonna rule. You are gonna move here. You are gonna cross. Every time you cross, there is overflow. You understand the idea? Any questions? Okay. So in case of sign numbers, that's what I told you. If I add 2 positive number, I get negative, or if I add 2 negative number, I get a positive number. There is another way. We're going to use it in the hardware, this other way. The other way is you can observe. For now, you can use the first approach. It's easy, but there is an equivalent approach. We are going to use it later in the hardware. You can observe 2 carries, okay? 2 carries. For example, I have a number this way. You can see if there is a carry here. I'm gonna call it, for example, C2. For example, also I'm gonna see if there is a carry here. So the last 2 carries, okay, from the carry out of the most significant bit and the carry enter the most significant bit. I'm gonna call it C1. Is that okay? This is another approach. Okay, I'm gonna look at these 2 carries. If these 2 carries are the same, that means if C1 equals C2 is equal to 0, or C1 equals C2 equal to 1, if they are equal, so there is no overflow. If these 2 carries are not equal, an overflow happens, okay? Are not equal means one of them is 0 and the other one is 1. Okay, and anyway, for now, okay, so these are 2 approaches, they are the same. You can, for now, it's easy. For now, we may need this one, but later when I design the hardware circuit, and I want to know if there is overflow or not. So actually, I'm gonna use what we call exclusive OR circuit. Okay, as I'm gonna explain later. So I'm gonna input here C1 and C2. Okay, because this circuit should give me 1. This circuit should give me 1 when they are not equal. When the 2 inputs are not equal, give me 1. Okay. Anyway, so it's the same way. So you can. Okay, let's show you here in one example. So here, look at this example. Again, I want to add again, you can add these numbers normally. So 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 1 is 0, and then we have a carry here, okay? And then 1 plus 1 is 0, and then we have a carry here, okay? 1 plus 0 is 1, okay? So number 1, is there overflow or not? Very simple, very easy. Look here. This is a positive number. I added it to a positive number, and then I got a negative number. So there is overflow. Very simple, very easy. Okay. And you can see the result here. I added 12 plus 5, and then I got minus 15. Okay. The other approach that you don't need to care about it now, but just for learning, because we're going to use it later. The other approach is, you can see, look at the most significant bit, okay? There is a carry input coming here. So C1 is equal to 1, there is a carry. However, there is no carry output here. So C2, for example, I'm going to call it C2, whatever the name. So the carry input and the carry out, I'm going to compare them. If they are different, so that means there is overflow. Okay, so here we have 1 here, but there is no 1. That's what I said here. if they are not equal and over, yeah, so here they are not equal because this one is 1, this one is 0. If they are not equal, so there is overflow. This is another way you can do it, okay? So also to understand how things work here, again, because the problem happens because, look here, guys, we have a boundary here, okay? So this number is -1, okay? And also we have a boundary here between, this is a positive, as I explained last time, this is a positive numbers, and this is a negative number. So what happens is that, or the reason, I'm just explaining what happened here. As long as you add two positive number and you are still in the positive area, you are okay. Look, I'm explaining how the problem happened. I'm gonna add two numbers. If you are still in the positive area, you are okay. If you add two negative number and you are still in the negative area, you are okay. The problem happens if I add two positive number and I cross here, okay? And this happens because you add binary numbers. You got what I'm saying? For example, that's exactly what happened here. I started from 12, which is this one. This one is 12, and then I added 5. When you add 5, 1, 2, until now you're okay. 3, you're okay. 4, the problem happened here because you crossed to the negative area. You got what I'm saying? That's a problem happening. Anyway, one more thing, as I explained last time, guys, and this is also, I know it may be a little bit, I'm repeating it because I know it may be a little bit confusing to students. If this number here, because this also will be in the test, okay, on the quiz and test. So this number are signed. Is that okay, guys? So how I was able to tell this is -15, as I told you last time. Okay, so as I told you last time, if this number is signed, but it is a positive number, so the last bit is 0. If the last bit is 0, like for example, this case here, the way you have to convert it, the standard way, the straightforward way, I have to multiply. So here the weight is 1, the weight is 2, the weight is 4, 8, 16. Okay, you have to multiply every digit by the weight. So if I do that, this should be 8 plus 4, which is 12. Okay, if it is positive number. However, if it is a negative number, okay, you have to get the positive version of this number by calculating the 2's complement. You get what I'm saying? Don't multiply the weight. Okay, so that's what I said last time. So here, to do that, number one, I have to calculate the 1's complement first by flipping the bits, and then you add 1. So these two numbers are the same as a magnitude. They are the same, but this is a negative and this is a positive number. Because this is a positive number, I can just multiply the weights together. Okay, so this number is actually, if you multiply 1, 2, 4, 8, if you add everything together, you get 15. So this 15, this one should be -15. Is that okay? But if this number is unsigned, you just multiply the weight. Okay, it's similar to the positive case here. Any questions? Okay, I just give you another example here. So here I add a negative number to a negative number, and the result is a positive number here. For sure, something is wrong here. You can see also here, if you add 0 plus 1, you got 1, and then there is no carry. So this carry is 0. Okay, 1 plus 1, and then this carry is 1. Okay, so now the two carries are different. Because they are different, there is overflow. Okay. Again, I just give you several examples here. Okay. I give you several examples for signed and unsigned numbers, and I just want to tell you here is there is no relation between unsigned overflow and signed overflow. There is no relation. What do you mean? I mean, if you consider the numbers unsigned and there is overflow, that doesn't mean there should be overflow if they are signed. There is no relation. That's why here intentionally I selected examples here to show you both signed or unsigned, both overflow. Or this one has overflow, but this one doesn't. This one has overflow, or both of them doesn't. So there is no relation between them. Okay, so anyway, so here, for example, here, if the numbers, let's start with unsigned numbers. You can see here, after I did addition, I found a carry. So if there is a carry, so this number, there is overflow. Okay. But in case of signed numbers, because here I'm adding positive to negative, don't think about it. You add positive to negative, don't think about it. So there is no overflow. Okay. Let's look at this case here. I'm adding positive to negative. So in case of signed numbers, there is no overflow. Okay. In case of unsigned, because there is no carry here, also there is no overflow. So for signed or unsigned, there is no overflow in both cases. Okay. Anyway, I give you also another examples here. So here we found in case of unsigned, there is it's correct, no overflow, but there is overflow in case of signed. So I want to just go through this example. If you can understand this example, I'm quite sure you will be able to solve the question in the quiz, also the question that will be in test number 1. Any questions? Okay, good. So the next part here, I'm going to talk about what we call binary code. Okay. So what do you mean by a code? Code means you have a pattern of zeros and ones that is used to represent an element of information that is distinct among a group of quantities. Okay. So it's just a pattern of ones and zeros. Okay. That used as a code. Okay. Or to represent an element in a group. Okay. So, for example, the very famous codes or the very is the ASCII code. I'm quite sure you are familiar with the ASCII code, the idea of the ASCII code. So the idea of the ASCII code is we as human being, we have letters. So we have A, we have B, we have asterisk, we have dot, we have letters. As you know, hardware or computers cannot understand these letters. They can only understand numbers, 0 and 1s. Is that okay? So what happens is that when you, if I want to input A to the computer, I have to convert A to a code, to correspond to code, which is a number. Is that okay? Same thing if this is the keyboard is entering a number to the computer, okay? So when I press letter A, so here you have to input a number because computer can only understand numbers. It's opposite when the computer want to display something on the screen, it has to send, for example, I want to display A, so I have to send to the ASCII of A, which is a number, okay? So it's very simple. So it's ASCII code is actually a table, as you will see here, it's a table. This table, every letter we're using has a corresponding number, okay? So as you see here, for example, here, even if it's a special letters here, every one of them has a number here, hexadecimal. So I give you the number in hexadecimal here, okay? Even numbers, by the way. So, so when you enter 0, I think something is wrong here. I think it's the other way. Yeah. So here, hexadecimal first, and then the value of second. So here, for example, yeah. So this one is actually 21. This one is 22 in hexadecimal. So this is the number we are going to enter for sure as a binary, as I told you before. So here I'm saying hexadecimal, but actually because it's easy for us to remember hexadecimal, but it's going to be entered to the computer in binary. So you can see everything here has equivalent. So when you press asterisk, okay, the keyboard is going to transmit 2A to the computer. If the computer want to display on the screen asterisk, it has to send the code 2A code. Okay. So all of them, even the numbers here, our numbers. So when you press 0, you are not going to enter 0. You are going to enter the ASCII of 0, which is 30. The ASCII of 1, the ASCII of everyone here. Okay. Even letters here. So you can see here, uppercase A should be 41. Okay. But a small a or lowercase a, 61. Okay. So uppercase, and so every letter, even space, I think you can find space here somewhere. Even space, I think space was 20. Okay, let me see here. Is that written here? It should be, yeah, space, this one here. Even space has ASCII of 20. Anyway, is that okay, guys? So this is a very good example for what I mean by a code. So code means you have a bunch of ones and zeros. This is a code. Okay, you have a bunch of ones and zeros. So for example, this one is 0010, which is 20000. This is a code. So this code is actually representing space. Okay, this is binary code. Okay, we use these codes in other things like BCD codes, gray code. I'm going to talk also about gray code, error detecting code, other. So, for example, here I'm going to explain gray code. Okay. So, and also we have here what we call BCD code, by the way. Okay, anyway. So usually, if I want to represent the number 0 in binary, okay, so for example, I have number from 0 to 15. So actually, I have to represent it in BCD code this way. One will be the same like this one. It will be something like that. Two will be, two is not going to be, this is different. Look here. Two should be 0, 1, 0, 1. Sorry, 0, 0. So because the weight here is 1, 2, 4, 8. So this is BCD code. So if the 4 bits, in the 4 bits here, for example, 15 in the BCD code is actually 1, 1, 1, 1. Okay, because the weight is 1, 2, 4, 8. Okay, but in Greek code we have something different here. So what I want to say is that if you have 15, so I'm going to use this code to represent 15 if you are using BCD code. But if you are using Greek code, I'm going to use this one. So I'm going to use pattern of 1 and 0s to represent a number here. So what is the main advantage of the Greek code? Why over the BCD code in this case? I'm going to tell you here. But anyway, in general, again, here I'm just defining what I mean by a code. Okay, so a code means you have just a pattern 1s and 0s to represent an element in a group. Okay, but the way I did it here, we call it Greek code. The main advantage of the Greek code is if you look at from one number, any number to another, you can see only 1 bit change. There is only change in 1 bit, not 2 bits or more. Only is a change only in 1 bit. Okay, this is the main advantage here. So always you see the change happened here. Here from here to here, there is a change only happen in 1 bit. So this is the main advantage of the Greek code. Why this is an advantage? In some cases, I'm going to tell you why. Because, for example, if I want to move from here, from this one to this one, this is BCD code, and this is actually number 7, and this is number 8. So if I use, I just want to give you here example why sometimes it is better to use the Greek codes than using the BCD code. So I give you here one example. If here this one number 7 and then I move next one to 8, so how many changes should happen here? This number 1, this bit has to change, this bit has to change, this bit has to change. 4 changes, right? So four bits have to change when you move from 7 to 8. What happens is that sometimes it depends on the hardware circuit you have. Sometimes to move, sometimes this bit is coming from a switch or coming from somewhere. So sometimes, so the 4 bits should change, 4. But sometimes one of them may be faster than the other. Because one of them faster than the other, before I move from 1110 to 100, I'm going to get something in the middle for some time, for a short period of time. Okay. And this is error. So for example, because before I move from here to here, it may happen that I'm going to get a number like this one for short period before you move from here to here. Okay. Because some switch are going to change faster than others. You get what I'm saying? But we don't have this problem here. We don't have this problem here because only 1 bit is going to change. The other bits are not going to change. You get what I'm saying? So I'm not going to get something in the middle when you move from one bit. Anyway, I don't want to spend much time because here I want to make a definition. What I mean by a code, binary code. So binary code means just a pattern of 1s and 0s, okay, to represent an element in a group. Okay. So anyway. After the last part here, I'm gonna talk about binary systems. Okay, so before I talk about, I'm gonna tell you something really very interesting. This course is really very interesting if you like it, if you understand it. Okay, so look here, guys. You know the algebra, the normal. I'm gonna call it normal algebra. I don't know if it has any other name. I'm gonna call it normal algebra. So the algebra you have learned so far. In this course, we're gonna have a different type of algebra. It's called Boolean algebra. Boolean. You know the word Boolean means 0 or 1. Okay, so Boolean algebra. Don't be scared because it's not completely different algebra. You will find there are some similarities between them, but also there are some differences between them. Okay, so here in normal algebra, you can have a function, like for example, I can say f of x and y. So this is a function in x, y, for example, equal xy or equal x plus y. Okay, I can have a function f of x, y, and z. Okay, for example, this one can have xy plus yz. Okay, something like that. This is the normal algebra we have? Is that right? So in this normal algebra, number one, we have function in number one, you have variables, right? These variables like x, y, z variables, okay? And also using these variables and using the variables and using the operation like addition operation, subtraction operation, multiplication operation, division operation. So using variables and this operation, addition, subtraction, multiplication, division, I can create a function relation. Is that okay? Relation between input and output. Is that's okay, right? You know, this is normal algebra. Is that okay? Now, here in logic circuit, I want to do the same thing. However, look at the differences. Number one, here, do you have variables? Yes, you have variables. So I'm going to have x, y, and z. Yes. So what is the difference between the two variables? Very simple. Here, x and y can be a number from negative infinity to positive infinity. Is that right? Here, this variable, every variable can only be 0 and 1, binary. This is the first difference. So the first difference is in the Boolean algebra, I'm going to explain in this course, we need in this course, number one, we have variable, but every variable can only be 0 or 1. Okay, this makes many things easier. Number one. Number two, okay, so number two, do you have operation like addition, subtraction? Can I use addition and subtraction? The answer is no. Okay, we're going to use here logic operation. So instead of doing addition and subtraction, multiplication, okay, like the normal algebra, here we are going to use logic operation. So that we have three main logic operation I can do. We can do not or inverter, we can do and, we can do or. Okay, so instead of doing addition, subtraction, multiplication, we are going to do this or the operation. We are going to do not or inverter and or operation, logic operations. Okay, similar to addition and multiplication, but we don't have here addition. Number three, can you create a function? Yes, because I have a variable, I have operation, so I can create a function here. So I can simply say, for example, f of x, y, and z, this function should equal to x and y or z. Yes, or z prime or z prime. This is inverter. Okay, so you can see here I used and, I used or, here I used inverter. Okay, this is not multiplication. This is another operation. It's called and. This is another operation called or. This is another operation is called not or inverter. Okay, and the result, this function is actually the result of it 0 or 1, because the inputs are 0 and 1. Also, the output of this function is 0 and 1. Okay. So here, these variables can take number from negative infinity to positive infinity. This function also can take values from negative infinity. It depends on the range or the domain of this function, whatever. But still, you have a big range, okay, whatever it is. But here in our case, all variables can take only 0 or 1, right? We can only use this operation, okay? These are the basic operation we are gonna use. Also, we are gonna create functions, and the result of these functions is 0 and 1. Any question? Did I explain it quickly? You understand what I'm saying? So what I'm saying here, I made a comparison between the algebra you learned before and the algebra we're going to explain here in this course. We call it Boolean algebra. We still have variables, but the difference is these variables are going to be input to a circuit, and the circuit is the function itself. So I have input here to the circuit, which, for example, x, y, z, and then I have here f of x, y, and z, and then I have output here. Okay. Sometimes we have one output, sometimes two outputs, whatever it is. But most of, at least in this chapter, I'm gonna talk about one output, but sometimes you can have two outputs. Every input or output is actually 0 or 1. Okay. Cannot be anything. Zero, binary, 0 or 1. This is number one. Number two, we don't have addition. Although we use dot and use plus, but this is not multiplication. This is not addition. This is or, and this is and operation. That's over. And also we use x prime. We use prime here to represent inverter. That's, these are the operation we have. Any questions? Okay. Okay, so now, so that's what I'm explaining here, guys. So we have here, we have what we call a binary system, or so by in for example, this is that's what I'm going to explain details in this course. So here we have a binary circuit, as you see here. In this circuit, okay, we have two inputs or two variable A and B. So these two variables, everyone can be 0 or 1. Okay, and then I have three outputs, as you see here. Okay, so for example, in this circuit, that's what I'm going to explain later in this course in details. I have 2-bit input A and B. If this one can be one, if this one is 1 and these two are 0s, that means A is greater than B. Okay, if this one is the 1 and this one are 0s, that means A is equal to B. If this one is 1 and the other two are 0s, that means A is less than B. So this is a comparator. I input to 1 and 1. And then the circuit here, for sure I'm going to teach you this case. The circuit here is going to tell you which one, if it is greater, less, and so on. Same thing here. We're going to use here. We're going to use some logic circuits here, and then we have input. So for example, I have 3 inputs here, A, B, and C. I have 3 inputs, okay? And the output here is going to be summation, because this is addition. Okay, so you have input, you have output. Again, the input always, any variable input or output should be 0 or 1. Always, we are talking about binary. You are not going to see in this course anything other 0 and 1. Okay, so no, nothing else. Same thing. So we have here 2 output, and then inside here we have a function. Okay, and actually we do it using what we call gates. But someone can tell me, okay, or you can tell me now. I told you now we have 3 basic operation. Okay, basic operation. Number 1, inverter. Okay, and we have AND and we have OR. Okay, so this is a symbol, as I'm going to explain, for AND. This is a symbol for inverter. This is a symbol for OR. Okay, what about this symbol? This one's here. Okay, so actually what we'll do in this course, I made it very easy. I said we have 3 basic operations, but using these 3 basic operations, I can make new gates. Like for example here, NAND, okay, like NOR, like XOR, okay, or sorry, this is XNOR or XOR. So what I'm saying here, guys, is so how I made this one here using the 3 basic operations. You understand what I'm saying? So using the 3 basic operation, I'm gonna make new gates. Okay, but everything is created using the 3 basic operations. And then once I created this way, so this one actually AB, so this is A and B, everything inverted. Okay, so you can see here. So then I'm gonna use it as a standalone gate, as a gate, right? But every gate I'm gonna explain here in this course is actually created from the 3 basic gates or the 3 basic operations. I'm gonna explain. Any questions? So let's start with the 3 basic logic operation or logic circuits. Okay, let's start with the first one here. The first one, we call it inverter, or we call it NOT gate. This is a symbol. This is a symbol of it. Okay, you should have a bubble here. This is how it looks like. It has only 1 input. It has only 1 output, as you see here, and the output is actually the complement of the input or flip of the input. That means very simple. This is how it works, I think. Okay, I think, yeah. Okay. So this is how it works, guys. Is if you input here, it's only 1 input. Is that okay? Only 1 input. This input has 2 cases, either 0 or 1, nothing else. So if the input is 0, I'm gonna get here 1. If the input here is 1, I'm gonna get 0. Logic 0. Okay. So if the variable of the input is gonna flip the 1's complement. Okay. So the input is only 1 bit. This bit is gonna flip it. If 0 becomes 1, if it is 1, it becomes 0. Okay. So this is 1 gate here. We have another gate. We call it OR gate. We have another one, AND gate. And as I told you, everything we're gonna build using these 3 basic logic circuits. I want you, and that's what I explained because in the coming lab, you are gonna have a chip. This chip has it has 6 inverter inside the same chip. Okay, it has 6, but you don't need to use all of them. Okay, so you can use only one. So that's what you'll see in this course. If you have a chip, the chip, for example, may have 4 or 2 or 3, whatever, a certain number of AND gate. Okay, you can use 1, you can use 2. You don't need to use all of them at the same time. You don't need, right? They are separate. Okay, but anyway, that's what you should see in the coming lab. So you can see here in the coming lab, in this chip we have 6 inverters. Okay, very important thing, guys. Okay, I want to connect just to see the big picture. I want to connect this course to two other courses. Okay, to see the whole picture. Okay, electronics. I'm not going to teach you electronics, okay? But you should understand there is electronic big background of it, because everything you are going to do it using transistors, using electrons. That's what you have. You should understand, okay? Using voltage. Here, I'm using 0 and 1 as logic 0, logic 1, okay? But as you will see in the coming lab, and as we explain in this course, this 0 and 1 ones have voltages in electronic. Okay, so here I just use it in this course. I use it like a simple, like a logic circuit, okay, but not electronic circuit. In reality, this one internally this one is created using some kind of electronics, and maybe you are gonna learn in other courses how can you do that. So, for example, this is the inverter. For sure, I'm not gonna teach electronic, but I just want you to understand. Everything we have here has electronic background. It's built by electronics, okay? But I'm gonna just use the logic functionality of it, okay? So, for example, if you have transistor here, whatever the type of the transistor you are using, you have here 5 volt. If I input here 0 volt, so, okay, 0 volt, so the transistor is off, open circuit. Because it's open circuit, so the output here will be, and this current is very small, you are going to get here 5 volt. So every time I input 0 volt, the transistor is going to be off, and then I'm going to get 5 volt. You got what I'm saying? So 0 volt is equivalent to logic 0. 5 volt is equivalent to logic 1. So I give logic 0, I got logic 1. Okay. Anyway, same thing here. If I give the circuit here 5 volt, the transistor becomes a short circuit. It's connect like a switch. Yeah, open or connect. So here it's gonna connect, and the output here will be 0 volt. So here I give 5 volt, I get 0 volt. Okay. Anyway, forget the electronics, but you just should understand. Because when you read the data sheet of the chips, you will see they are talking about transistors and stuff like this. But this can be taught in another course. In this course, I'm only focusing on the logic part of it. I have an inverter. I don't care about how it is made. The functionality of this inverter is you give 0, you get 1. You give it 1, logic 1, you get 0. Is that okay? Okay, one more thing you should understand. There is, I told you here in case of the inverter here I have logic 0, logic 1. This is the logic. Every logic here has voltage, equivalent voltage when you talk about the implementation or electronic. Usually, logic 0 is going to be equivalent to 0 volt, and logic 1 is equivalent to 5 volt, and that's what you see in the coming lab. Okay, so but to be more specific or to be more accurate, it's not only one value, it's a range of values. For example, I think that's what I'm explaining here. For example, if you have an inverter, if you input, so here any voltage in this range between 0 and 0.3, so this one is considered logic 0. So if you input here any value between 0 and 0.3, so this is logic 0. Okay, a range, anything in this range. Same thing for logic 1. Logic 1 is not only one value, but also a range. For example, just an example, 4.3 to 5, anything in this range. Most of the time, we're going to say 0 volt and 5 volt, but it's okay if you, as long as you are in this range, it's going to act as logic 0 or logic 1. Is that okay? Someone can tell me, okay, so if I have an inverter like this one, I should only input a voltage, either a voltage in this range or a voltage in this range. Yeah, that's true. What about this range? You should not use. Otherwise, it's not going to be logic circuit. You get what I'm saying? You can play at home. You have the shapes. You can be, it's not, you're not going to burn it out, but you can try. If you give something here in this range, what will be the output, right? But you should not. The input has to be either in this range and this. By the way, and also that's what I explained in the video. This value 4.3, is that a magic number? 4.3. The answer is no. It depends on the chip itself. That's why if you read the data sheet, there is something, that's what I explained in the video. This specific number is written in the data sheet of every chip. Okay, it's called V input. This is V input high. So you can find it in the data sheet. V input high is actually the minimum voltage that can be considered logic 1. Okay, watch the video. I already explained in the video. For same thing here, this one, 0.3 is not a magic number. So it depends on the manufacturer. It depends on, so it can be something else other than 0.3. Okay, you can tell from the data sheet. So this one actually is called V input high. Okay, so you will find it in the data sheet, V input high. So V input high is actually the maximum voltage that can consider as logic 0. Okay, guys. Again, what I want to say, what I said, I want to link this course to 2 other courses. Number 1, electronics, as I told you, because we have electronic background here, but I'm not going to teach any electronics in this course. Okay, we are going to only talk about logic 0, logic 1. Okay, so I'm going to see it like logic, not voltage. Okay, and then I'm going to assume I have a hardware circuit that can do this functionality for me, and that's true. Okay. The other course also, I want maybe a little bit early, but there is also other course, as I told you, I think in first lecture. In this course, I'm not going to teach a computer system or a digital system, not a complete system. So the purpose of this course is just to teach some devices or basic devices that are used to create a computer system. You understand? So I'm going to teach register, how we can make a hardware register. I can teach how can you make multiplier. I can teach how can you just separate elements. Okay, but we're not going to put everything together. This may be another course, computer architecture or something like that. I'm going to teach encoder, decoder. I'm going to teach how these devices are working, what they are doing. But actually, what happens when you go to another course, no one will teach you how to make registers, because this is the purpose of this course. Okay, they just will use. We have a decoder, we're going to use it. We have a register, we're going to use it, and then you should learn this basic devices. Any questions? Okay, good. So look here, guys. So now I'm going to teach, I already taught this one, inverter. This is a symbol. It's always, we have one input. We always have one output. It's inverted as we see here. Is that okay? There's also something important. If you have logic circuit, and I want to know how the circuit behaves, okay? How the circuit behaves. To do that, usually we do one of 2 things. Either what we call it truth table, okay? Truth table, or we do timing diagram. So again, so how because we're going to do this one. This is a very simple case. So you can see this one like a function or a circuit, logic circuit, but it's a very small circuit because you do only one operation. But that's what we're going to do even in the future. So even if you have a big function, okay. But this one, you can see it like a digital circuit that has only one input, one output, okay. But usually to represent or to how it behaves, all what we do, truth table. So what is truth table? Because that's what we're going to do all the time. In truth table, guys, is you put all the inputs here and you put the outputs here. And you put all possible cases for the input and put all possible cases for the output. Okay. If the input is 0, I'm gonna get whatever. If the input is 1, I'm gonna get whatever. Okay. Again, this is a very simple case because I have only one input. So if I want to mix a truth table for the inverter, all what I'm gonna do, I have only one case, one variable which is x. So this is the input, and we have here one output. We have only one output. Okay. What x prime. Okay. So now. This is truth table. So in the truth table, You have input, you have output. You have to put all possible cases for the input, and then you have to calculate all possible cases for the output. Is that okay? So because we have only one input, so this input have only two cases, either 0 or 1. That's it. Very simple. This very simple case. Okay. If the input is 0, so the output has to be 1. If the input is 1, the output should be 0. Okay. So this is a very small truth table. We are going to create this truth table in big cases. Big cases like, for example, here, if you have, for example, here, I have three variables, these 3 inputs. So I'm going to tell you how can you make all different combination here for input, and for every case, what is the output here. It's easy now. Why it's easy now? Because comparing to the normal algebra, because I have a limited number. Every variable can be 0 or 1. You get what I'm saying? So I can make all different combination here. It's easy to do it. But in normal algebra, you have infinite number of cases, right? Because every variable is going to be continuous, right? But here it's easy because every variable can be only 0. So this anyway, so this is what we call a truth table. Okay. So now there is another way to know or to represent the function, the functionality of any logic circuit. For sure, that's a very easy case, is using what we call timing diagram. So another way. So there are 2 ways, either using truth table like this case, or there is another case here. It is using what we call timing diagram. So what is timing diagram? And that's also what you do in the lab. Timing diagram. So as you see here, I'm going to have, for example, here. Okay, so forget this one here. Forget this one. Forget this one because this is AND, this is OR. Okay, so just look at these 2. So this is timing diagram. So timing diagram here, I have here, you can see here, this is the time, and this is can be logic or can voltage, but here it's not voltage or so here during this period of time, this period of time, input was logic 0. Okay. Now at this moment, the input jumped to logic 1, and then at this time here, so time, this is time here, time and logic. Okay, and now it becomes logic 0, and now it is logic 0. Okay, so what? So here, and then I'm gonna calculate the corresponding output. So you can see here, guys, when the input was 0, the output was 1. Makes sense? When the input was 1, the output was 0. Okay, you can see here. When it is 1, it was 0 here. At this moment here, it's gonna change, input change from 1 to 0, so the output is going to change from 0 to 1 this way. Okay, so this is another way. So the input can be all possible cases. For example, here in this case, it can be 0, and then it can be 1, something like that. And then the output in this case, this is the input. The output here should be, when the input is 0, so the output here is 1. Here is 0. Again, this is very easy case because I have only one variable, but I'm going to use the same concept. The same concept is, if you have any logic circuit, and you want to know how this circuit works, we're going to use one of 2 approaches. The first one is called the truth table. The truth table is going to give you all possible inputs. For every input, what is the output? For every input, what is the output? Is that okay? Table, in a table. Or the other way, I can do it in timing diagram. Any questions? Okay, so let's move to the next one here. We have another gate. We call it OR gate. OR gate. You can. Okay. OR gate. OR gate. It can have 2 inputs. Okay. Always it has 1 output, but it can have at least 2 inputs. So it can be more. So OR gate it's different from this one. This one always we have 1 output, one input. Always. Okay. If you have multiple input and you want to invert them, so you need to use more than 1. So for example, if you have X, Y, you understand what I'm saying? Z, yeah, I can invert all of them. I can do that. But every one gate, it has only 1 input and 1 output. Okay. So here for OR gate here, okay. For now, let's assume 2 input. I'm going to talk about more than 2 input later, but let's talk about 2 input. So we have here 2 inputs. Again, I don't need to keep repeating it. These inputs or variables are binary. Everything here is binary, guys. Okay. So every one here can be 0 or 1. 0 or 1. Is that okay? And the same thing for the output here is going to be 0 and 1. The symbol to represent this operation, the or operation, is plus, as you see here. So again, this plus is not addition. We don't have addition here. So in logic, we have only 3 operations: inverter, okay, or and AND. These are the basic operation. Is that okay? So this plus means or. So what or means? Okay, or how it works, how or works. I'm going to tell you very easy thing. If you come to me and, for example, you ask me about something, okay, how I can base this course, I'm going to tell you, you have to do either A or B. So what it means? It means one of them should be enough. If you do both, okay, that's more than enough. You understand what I'm saying? So this is the same thing here, or. So or is going to produce 1 if you can just satisfy at least one of them. If, in other words, if at least one input is 1, the output is 1. Because or, if you are using in our life, right? Or means you need to satisfy one of them. So this is how it works. So for OR gates, okay, if one input is 1, I don't need even to look at the other inputs. The output is directly 1. It's enough to have one input is 1. If possible, okay, that's more than what I need because it's OR. Okay, this is how it works. Okay, so that's why let's do the truth table of this one. The truth table is you have X and Y. This is the input, and then I have the output here. I'm going to call it Z, the output, where Z is equal X or Y. Okay, so number 1, you have to put all possible cases here. You have to put all possible cases. So how can you do? Number 1, how many possible cases you can have? You have 2 input. When you have 2 input, how many possible cases you have? As I told you before, if you have any bit number, all possible cases is 2 to the power of n. So in this case, yes, in this case, I have 2 input. So the relation, so how many cases I should have? 2 to the power of 2, which is 4. So I should have 4 cases. Is that okay, guys? If I have 3, if the input here is 3 variables, how many cases I'm going to have? 2 to the power of 3. If the inputs are 5, how many cases? 2 to the power, this all possible cases for inputs. Okay, that's true. Okay, that's number 1. Number 2, how I can find these inputs? Okay, I'm going to tell you a very simple approach. Look here. This one here, half of the space are zeros, half of the space are ones, and then you will see some pattern now. Okay, you will see some pattern. For example, look here. I'm gonna here put 0 0 1 1, and this one here 0 1 0 1. That's it. So now I have all the combination. So you will see in case of 3 bits, also there is some pattern you can know. Look here, in case of 3 bits. In case of 3 bits, how many possible cases I have? 2 to the power of 3 should be 8. This is our 8 cases. How I can do it? Look here. The last one here. So the half of the space 0, half the space are ones. Next one here, so it should be half of this one, half of this one, half of this one, half of this one. Okay, and until the last one should be 0 1 0 1. So there is a certain pattern you need to know. But let's now focus on this one, X and Y. So the pattern I have here, 2 zeros, 2 ones, 0 1 0 1. Is that okay? Or you can start, if you want to start right to left. So here, the first one here, 0 1 0 1. The next one, 2 zeros, 2 ones. If you have something after that, 4 zeros, so it's 1 0 1 0 here, 2 zeros here. The next one is going to be 4 zeros, 4 ones. The next one is going to be 8 zeros, 8 ones. Okay, you know. But I think it's easy to take it left to right, so you can put half here, and then next one should be half, and so on until you reach 0 1 0 1. Anyway, so these are all possible cases I have. Okay, so again, you should understand we are going to use the truth table all the time. This truth table, guys, is going to explain to you how the circuit works. This is a very small circuit because we have only one gate, but in the future, when you have multiple gates, something like that, we have a big circuit here. This circuit has 3 input, and we have several gates here, and then we have output. It's the same idea. Also, we're going to use a truth table to learn how it works. Also, or you can use timing diagram. So anyway, as you see here, input 0 and 0. 0 and 0, this is the only case that can give you 0 in case of OR. Okay. Again, in case of OR, if at least one input is 1, it's enough. The output is 1. Don't think about it. Here, I found the 1. Don't think about it. It's 1. I found 1. Don't even look at the other one. It's 1. So if you find one input is 1, don't even look at the other one. It's 1. Okay. That's why this is the truth table here. So the truth table gives you the relation between all possible input and all possible outputs. So this is one way to represent it. Again, there is another way, which is using timing diagram. So as you see here, we have X here in the timing diagram. In the timing diagram, guys, is just visual representation of the truth table. Okay. So as you see here, guys, here we have 0, 0, which is actually the first case. And then here we have 1, 1, 0, which is the second case. We have here 1, 1, okay, which is one of the cases here. So anyway, so this you can see it like a visual representation to the truth table. So if this X and Y, so I forget this one. Okay, forget this one. So it's going to be this one. So look here, guys. We have here 0 and 0. So the output should be 0. Here at this moment, you change it to 1. As long as this one is 1, I don't even think about the other. So this one has to be 1. Here we have 1. I don't even need to look at the other one. So it has to be 1. Okay, this one is 0. So now I have to look at the other one. You understand what I'm saying? So if you find 1, you don't need even to look at the other input. If you find 0, so now I have to check the other one because I need 1. You understand what I'm saying? So here I found this 0, so I'm going to look here 1, so it has to be 1. 0, 0 should be 0. So again, you can here I explain the functionality of the circuit using in a visual way. It's the same thing like the truth table, no difference. Okay. Any questions? Okay. Yeah, sure.
How do you? I noticed with the OR gate, how would you add with using these 3 things, like how we binary addition with overflows? The OR, it says X plus Y, but it doesn't look like when adding them there's any carry.
Okay, this is a very good question. I want to tell you something. This operation, we don't have addition or multiplication like the normal algebra. We only do 3 operations, inverter, and then we are going to do OR operation or AND operation. Okay?
Okay.
Using these 3 operations, we are going to do everything.
So there's separate operations for it.
Yes. So for example, yeah, regarding your question, how can you do addition? This is a circuit I'm going to explain in this course. This is the one that can do addition. So I'm going to explain later in details. Okay. So you need using the 3 operations, I'm going to do addition. But the circuit itself doesn't do addition. We only do these 3 operations. Is that okay? Okay, so I'm going to teach. We can do multiplication. So we can do some mathematical operation. You can do logic operation. You can do other operation using these 3 operations. Okay, good. So now, I'm going to move to the last one here. We have here, which is AND. Again, similar to our life. In our life, if you come to me, what should I do to pass this course? I'm going to tell you. You have to do A and B. And B, what it means? It means you have to do both of them. If you only do one of them, it's not going to work. Exactly same thing here. Same thing here. In order to get 1 here, both should be 1. You have to satisfy the 2 conditions. Both should be 1. If only one of them is 0, so that I don't even need to look at the other one. The output is 0. Okay, I'm going to say it again because it's like the opposite of OR. In case of OR, guys, look here. In case of OR, this is a symbol of OR. If one input is 1, I don't even need to look at the other one. The output is 1 right away. Is that okay? If one input is 0, okay, so now I have to check the other one. Okay, but the only way to get a 0 when both are zeros. This is for OR. For AND, if one input is 0, you don't need to check the second one. It's 0. The only way to get 1 here when both of them are 1 and 1. That's why let's do the truth table of this one again. So here we have 2 input, X and Y again, and then we have here Z, which is equal X and Y. I'm going to put all possible cases. The way I'm going to do all possible 0, 0, 2 zeros, 2 ones, because the whole space we have 2 input here. So how many different cases you have? 2 to the power of 2, which is 4. So half of them zeros and ones. Okay, and then 0, 1, 0, 1. So by this way, using this pattern, now I have all possible cases. So now let's do it. How can you do it? Very simple. If you follow what I'm saying, you can do it very quickly. Okay. Again, one input is 0. Don't even think about it. The output is 0. Okay. One input is 0. The output is 0. Don't think about it. One input is 0. The output is 0. The only way to get 1 when the two inputs are 1s. Okay. So this is how can you do it using truth table. I can visualize the truth table using what we call timing diagram. So this is the time and this is the logic is here. Okay, so I can do the same thing here. For example, here you have X and Y. Okay, look at this ones here. And this is, so if you see here, guys, during this time, the input. By the way, this is the input you are going to generate using the function generator, using the discovery kit. So using the discovery kit, you are going to generate this signal, you are going to input it, and then you are going to get the output, something like that, and then you can visualize it using the scope. That's why you need function generator and you need a scope. Okay, and this is in the discovery kit. So discovery kit is going to enable you to generate signal, also enable you to see signals. Okay, anyway, so if you see here, guys, if one input is 0, the output is 0, regardless of anything else. I found it 0, so this is 0. Here I found 1 and 1, so this one should be 1. Okay, this is the only case that can give you 1. So 0 is 0, 0 is 0. Okay, any question? Okay, so what I just quickly in what I did here, guys, I explained 3 basic operations. Using the 3 basic operations, we are going to do everything. Okay, every operation using these 3 basic ones. Okay, so what I'm going to do next time, I'm going to explain how can we make functions. For example, you have X, Y, Z. You have 3 input X, Y, Z. How can we create a function? And in this function, I'm going to use inverters. I'm going to use AND. I'm going to use and so on. So you can see here. Wait a second. Just give me 1 second. So here we have input. I'm calling it S. So this one is S prime. This is A. So this one A and S prime. This one is S and this one is B. This one S and B. So Z, which is actually F of A, B, and S. So I have 3 inputs here. So the output of this function is A and S prime or S and B. Okay, this is a function. I created a function using Boolean variables, okay, and using this operation. And then I can create a truth table like this one. First of all, here I have 3 variables. So how many cases you have? You have 8 cases. So you can see here, 4 ones, 4 zeros, 2 zeros, 2 ones, 2 zeros, 2 ones, 0, 1, 0, 1, 0, 1. If you do this way, you are going to have all possible cases. And then what you can do now is you can just plug in. So this is S and this is A, and then you can get Z. So that's what I'm going to do next time. I will teach in details these functions. How can you create these functions? Okay, but this is a circuit. Sorry, give me just 1 second. So this circuit here is not doing anything, okay, just for education. But in the future, I'm going to create a circuit that can do comparator, can do addition, can do whatever. You understand what I'm saying? So this circuit has input, it has output. The truth table is going to tell you if for this input, this is the output, for this input, this is the output, and so. Okay, thanks.